My name is Jason Schroeder, and I will be presenting Imperfections in Solids as my final project for Intro to Materials Science. There is no such thing as a perfect crystal structure. As crystals form, there are many imperfections that cause changes to the crystal matrix structure and distort it in several different ways. These imperfections can fall into three different categories: point defects, line defects, and area defects. Point defects include vacancy atoms, interstitial atoms, and substitutional atoms. Line defects include screw and edge dislocations. Edge dislocations involve an insertion of a plane perpendicular to the crystal matrix. It can be seen in Figure 1 to the right. Screw dislocations involve an insertion of a plane parallel to the crystal structure. Area defects include grain boundaries. Grain boundaries are caused as crystals are forming, and as they grow and expand their crystal structure, they butt up against other crystal structures forming and cause the lines shown in Figure 2. Both edge dislocations and grain boundaries are common in crystal structure formation. For this presentation, we'll be focusing on point defects and their causes and effects of them. There are two main types of point defects: intrinsic and extrinsic point defects. Intrinsic are caused by atoms of the same kind as the atoms in the crystal structure. Vacancy atoms are empty sites within the crystal structure that can distort the crystal matrix. Self-interstitial atoms are atoms of the same kind as the crystal structure inserted into the crystal matrix. Extrinsic defects are point defects that are caused by atoms of different kinds from the atoms in the crystal structure. Substitutional atoms are replacing an atom in the crystal structure with an atom of a different kind. Interstitial extrinsic point defects are usually caused by smaller atoms that are different from the atoms in the crystal structure that are inserted in the gaps between the crystal structure. There are multiple effects to point defects, including changes in material properties such as mechanical, electrical, and thermal properties. While these effects can be negative, oftentimes they are also useful in different uses. An example of this would be doping silicon with phosphorus or boron atoms, which change its electrical properties to be advantageous for semiconductors, and creating both N and P semiconductors. Another example of this is diffusing carbon atoms interstitially into iron, which will increase the hardness of the structure. We're now going to look at a model of carbon steel where carbon atoms have been inserted interstitially into the iron crystal structure. For this model, the iron atoms have been arranged in a body-centered cubic structure, which is what iron crystals form at room temperature. The iron atoms are shown by the blue spheres, and the carbon atoms are shown by the red spheres. While for carbon steel, carbon atoms usually only make up about around 1% of the weight of carbon steel, it has been added just to show how the atoms would be arranged with a higher carbon percentage. As you can see, the carbon atoms are inserted interstitially between the cubic structure of the iron atoms, which allows the crystal structure to actually harden and be more resistance to have more resistance to movement or strain. Here are my references for this presentation, and thank you for watching.